All right, good evening. Welcome to another video. So, last video we finished out use case 4. So now we're on to use case 5. We're actually well over halfway done with the book. So that's definitely something to celebrate. Uh, use case 5 is the cabling in my network correct? One more thing to say about the last video, use case 4. I'm not doing this in the way the author wants. The author wants it to be done in Google Colab, which integrates with Google Drive. I'm doing it locally just because I'm that guy. I want to get it to work the way I wanted to get it to work. And if there's consequences as a result, it doesn't work. I want to, that's what I'm in it for. I want to see those error messages. I want to see things going wrong. That's I think where most of the learning happens. If you just follow it and it just does exactly the same thing and there's no error messages, nothing ever goes wrong, what are you going to learn? So that's my reasoning for that. I wouldn't recommend somebody else do that. You can actually damage your equipment. You can and it wastes a lot of time too. So I wouldn't recommend other people do that, but for me, I just can't help myself. So I had to take an L. I do that sometimes in books if I can't get the tutorial to work, but I have to do that with a caveat. It's by no fault of the author. The author made it very clear how to run this. I deviated off and didn't run it in that way, and it didn't work as a result. So still have high marks for this book. There was only one major impacting typo. There's a few typos here and there grammatically, word wise, but it doesn't make a difference. And the content's great. So high praise for this book so far. So let's continue on with use case 5. Is the cabling in my network correct? Pain point. Cabling is challenging, particularly in highly dense network locations such as cloud data center fabrics. A mistake in cabling may lead to connectivity issues, which may not be obvious to identify, since the topology view we may have from the network may be different from the physical connectivity. Having an accurate view of the network topology is very important. There are multiple methods for monitoring systems to achieve such visibility. Link layer protocols such as CDP or LLDP provide valuable information. And this might blow if you're a network engineer and you're only work with Cisco, it might kind of blow your mind to learn that there are other forms of proprietary link layer protocols. One is EDP, it's Extreme Discovery Protocol for extreme gear. So in my experience, just use LLDP. Unless you're in like a locked down hardcore Cisco environment, then you can use CDP. I think some of these proprietary protocols do have advantages over LLDP in that they can provide you with more information that is necessary to have. But LLDP is the open source one that all of the vendors will have. CDP in an open environment will only work with your Cisco devices. IP interface configuration or routing information are also helpful sources for higher level visibility of the routing topology. Some level of protocol support and interoperability is required in all cases, and they are OSI layer specific. Ultimately, these dependencies may create inconsistencies or lack of visibility in the topology. In those cases, back to the original pain point. If your view of the network is different from what the actual network topology is, operating and troubleshooting issues may be really challenging. It's like driving with a GPS that is not telling you the right position you are in. Yeah, and I've dealt with this a lot before. You can use LLDP, but if it's not set up, then you just get you don't get the information you need at all. So it kind of it can register as a false positive that. So you have to look at more than just the LLDP. You have to say, is the port up? Because if the port's up, line protocol up, admin up, passing data, then that's a live port with something on the other side, and either LLDP is not enabled on that port or it's not enabled on the other side. So it's not enough information to just get the LLDP information from a device, because you're going to get an incomplete picture. You should probably get the port status, especially and then you should get the traffic status as well. Is there actual traffic that is going across that line, even if it's just control traffic, just a few packets here and there. And that's where you're going to see a big difference too. Is there a flood of lots of traffic on this link, or is there just a little trickle? But that doesn't give you enough information either, because it could be a special, like for example, let's say it goes to an office. Office hours are 9 to 5. You check it at 10 p.m. There's just going to be a trickle on it, but then you would check it at a different time and there'd be a flood. So that's, you have to monitor it over time. This stuff is hard. I've tried to do this stuff before, and it's typically the people who do this have special access and special tools. So if you're like me, where you're just doing it because you can, and you won't break anything, it's gonna be challenging. But the main thing is stay out of config mode. Stick to those show commands. Don't break anything, and most importantly, get your actual work done. All right, so approach. The goal, therefore, is to find a mechanism that may be a universal topology discovery technique, one that does not depend on vendors, protocols, or network layers. Data comes to our rescue here, bringing us the possibility to extract precise topology information simply by looking at interface traffic. The approach discussed in this use case is based on existing public research. See 31 as example. So that's 31 is probably a citation in the back. One more quick thing to say about show commands, though. Depending on the device, not even running show commands could be safe. On some Alcatel Lucents, if BGP is not running on it, and you do a show command for BGP information, it will enable BGP. Now, enabling the BGP daemon with no configuration on it really doesn't do anything, but you're starting up a new process on the device where a process was not started up before, and that can have minor consequences, with the CPU memory that new process causes. And then the really critical thing is, if you see that, don't panic, raise your hands back away, because the worst thing you can do is be like, oh no, I made a change to the network that I did not intend. Let me try to undo that change. No, just forget it, back away. You got lucky, you didn't break anything. If you go back in and say, I'm gonna run my script again, but I'm gonna delete this all, that's where you can come into some problems. So if you're on a real production network, focus on your work. If you want to, do some things like running a script on the network, just be really, really careful. I'm not going to say not to do it, because if you can do that, it's a really good learning experience. But I am going to say focus on your actual work first and get that done, and then with the extra time you have, don't be invasive. Do it in a way that's not invasive. Just do a basic show command across your 100,000 million devices, and be safe is the main thing. All right, so correlation is very overloaded term. Oh, I didn't start this page yet. While this practical use case is not really about any machine learning algorithm, it is about data and how to leverage data and analytics, in this case, to extract topology information. The fundamental approach is based on the concept of correlation, or more specifically, Pearson correlation. Correlation is a very overloaded term that is used to refer to many different things. Strictly speaking, correlation is the connection between 2 points that are related. There are multiple types of correlation, and you might have heard people say correlation is not causation. So they might bring that up at some point. That's a common thing people will say in regards to correlation. In our use case, we will leverage the following facts. In most of the networks today, with the exception of Wi-Fi access and cell radio access, connections are point-to-point. There are no multi-access media anymore. Interesting. Given the above, unless there is some transmission issue in between, all traffic that is transmitted from an interface should be received on the other end. Seems a very obvious principle, but it is extremely valuable for our case. Considering this, when we make the assumption that if traffic leaving one interface is the same as traffic entering another interface and vice versa, we could state that they are point-to-point connected. Of course, there are nuances to this statement. When we say the same, we may need to relax the condition and say very similar. But what does very similar mean? Volume of traffic? It could be one option, but it leaves a lot of information that may lead to wrong results. We have a mathematical mechanism to determine how aligned two metrics are, which is the Pearson correlation. The Pearson correlation index measures the extent to one metric is linearly dependent from another. When there is a strong positive linear relationship, the Pearson correlation will be 1 or very close to 1. When the relationship is negative linear, the index will be -1 or very close to it. If the metrics are completely independent, also referred to as orthogonal, the correlation index will be 0. In our case, if one interface is connected to another and we measure the correlation between egress and ingress traffic on the other end, the result should be 1 or very close to 1. Whereas if we calculate it against other interfaces, the shape of the signal will have variations that will lead to a lower correlation. Based on the above, if the Pearson correlation index between egress and ingress in one direction, and the same for the reverse direction, for two interfaces, is very close to 1, we can state that they are connected. We will use this hypothesis to discover the network topology in our SANS generated simulation environment. And I've done home office videos on this channel, which I'm pretty proud of, because that I think that'll help a lot of people out, because I've come to this setup over many years, and I'm using exercise equipment. But I'm a little bit hesitant to make that video because my exercise goals are not coming along very well. But I do have a lot of pretty awesome gear. The problem is I'm just not sure if it works or not. I know that my keyboard and my headset have been very valuable, my headphones, but my exercise equipment doesn't seem to be doing what I want it to. All right, but so that's that delay. I'm setting up I'm putting a stretchy band around my ankles and then walking on a treadmill. Input data. As indicated, Our input data for analysis will be exclusively input and output traffic. How it is measured: bits per second, Gbits per second, packets per second, percentage utilization. It is not really relevant, but of course, we need to make sure we use the same measure across all interfaces. In order to limit the computation complexity of the exercise, we will focus on discovering the topology of the core between PE devices and C devices. We will request SANS to provide us with traffic for all core interfaces on PE and C devices for a limited period of 10 hours. So this should look familiar. This is what we do to get data frames from SANS. So this is where I will change gears a little bit and open up Visual Studio Code and run this. And I will run it on my local again. It's not the best way. We ran into issues in the last one doing it, but okay. So I've got source control here. I made a lot of changes here. You know what? Let's do a commit on that. So we're going to do get status. We're going to do get add, get commit, -m. We're going to do end of use case 4. Okay, and then we're going to do a get remote -v. Okay, and now we can see if I push this, it'll go to my repo and not the author's repo. So let's do a get push. All right, and I should have done it beforehand, but I also want to do a get branch to see what branch I'm on. I think I'm on the main branch, but I might have created my own branch. Okay, I made my own. It's better to create your own branches because then you can create pull requests and have more comprehensive on Rails code reviews using the tools you get with GitHub. But it's just me. I'm not on a coding team, so this will be fine for now. All right, so it's time to move on to use case 5. There we go. And we've just got 2 files here. One is a Jupyter Notebook, so let's open that up and get rid of these dead ports here. All right, and then start Jupyter Notebook. All right. Use case 5, notebook file. And there we go. So I'm not using this because I want things to not work and to have it be worse. So that's my reasoning for that. So I'm going to get rid of this. I'm going to change these so that it runs locally. But again, I do not recommend this as a way for people watching this, especially if you don't have the hardware. All right, so we've got to add that import sys statement back in. Okay, and then we need to change this to use case 5. All right, and that should be good to go. Oh, one more thing. We have to change the import statement. There we go. And that has been good enough. We tried to train a model that would have taken 17 hours to train according to my calculations, and that failed. I ran out of memory on my computer in order to do that. So yeah, I am not the proud owner of a supercomputer, unfortunately. All right, so we're gonna restart and clear all output, and let's see where the book is. So the book is run. It has setting the parameters, and then probably running the data frame in the so it gets the data frame later on. So let's read and then get to that. SANS may generate anomalies in the metrics associated with programmed incidents. We have disabled this for this use case, the execution of the incidents. Why 10 hours and not more or less? At the end of the day, we need some level of information in the metrics to be able to compute the correlation index and make sure it is representative of their relationship and their differences. If you had only, let's say, 10 observations, the significance of such an index would be very low. All right. If you have 1,000 data points, but the variability is very low, the same issue happens, since the level of information carried in the signal is poor. In our case, we are using 10 hours that corresponds to about 120 observations per metric. Given the way we are generating the data and the randomness introduced, it is good enough to prove our point. If you wanted to try this with real network data, you may need more samples, likely somewhere between 200 and 400. Back to our generation. Like in previous exercises, we have a pre-generated data set in a CSV file. There we go. That can be loaded instead, since the data generation via SANS takes a little bit of time. Feel free to generate new samples or use the pre-generated data. So I'm going to generate a new sample. This is how the data frame generated looks like. All right, so let's get the data frame by running SANS and not loading in that existing file. So I'm going to comment out the line that would load in that existing file. Okay, so I think that's this line. So this would read the you know what? I think we're generating it here. We could test that by modifying the other file. We can see that I didn't run the other cells, so let's start over again with that. All right, that should be better. Now, what I'm doing is I'm loading in the file and not generating my own, but we see that's not the case because sans.generate is what we're running, and then we get the data frame from there. We save the data frame, so we'll be overwriting the existing one, and I can prove that's the case because I can save it as _1. Oh, no module named progress bar. Oh, we have to pip install it. Shoot, I can't drag that up. How do I insert a cell above? There we go. All right, so let's do pip install progress bar. Perfect. All right, so now we don't have that error. We just have the same errors as before. We don't have this network X either, so we just need to add that. And there's probably some other ones we don't have either. We'll just find it out through the process of running it. Okay, so yeah, we've got quite a few that are missing. I wish you would do a requirements.txt file. Okay, so now we've got that successfully loaded, and the cell completed successfully. Just those warnings that were there before. I just need to reconfigure my TensorFlow binary in order to get something that I probably don't need. Okay, so now we created the data frame. And we can see we've got that same warning for the .append method. So we could clean this up and have it be. So we can also use a older version of sans that we would not get this, or of an older version of pandas where we would not get this error. But let's just leave that to run. We're gonna run the next few cells. Now I need to change this to _1, and this will prove that what we're doing is saving the file, reading the file we saved, and running that. But if you want to, you can just load in the file that's already there. So then you just run. You can just run this cell, and you don't have to run these two cells here, as far as I understand. So we should eventually see a new file pop up in here. But in the meantime, let's get some reading done. In previous cases, there are more columns than those we need, but this is metadata useful for other use cases later in the book. For now, we will be focusing on the timestamp, traffic out MBPS, traffic in MBPS, and columns that help us uniquely identify interfaces, the unique ID, and device name. We are going to create two new data frames, one for egress and one for ingress traffic. All right. We can observe how the traffic data looks for a certain interface. All right. With this graph, it looks like that. As expected, output and input traffic for one interface do not look the same, and they do not have to. Okay, so this is still working. I think it's going to take a while. I think it does slow it down to get these messages, so taking out some of these messages I think would be helpful. I don't think we have to take out all of them. To take out some of them, it's not that hard. You just come in here and first find those. Yeah, and it's better to match on this because you'll get better hits. Now the reason I didn't keep my changes when I did this was because there's one instance of this where it's doing something special here with a entry in a list, whatever that data object is, I don't even know. And then it's taking the first index. So it's an indexable data object of some kind, but it's not a data frame. So if we just wholesale swap out append for concat, now we're going to have an issue with this line, and in fact all the lines, because concat only works with appending data frames to data frames. And we saw that in the last video. If I open Python 3 and I import pandas, and then I say df1, equals this data frame, and then df2 equals this data frame. Now we can do df1.concat df2 and see that it does not work that way. Data frame object has no attribute concat. So where is concat? It's in the actual module. So this whole statement has to change. It's no longer your data frame dot append another data frame. It's pandas dot concat df1 df2. And now it's even more complicated than that. If we look at the help menu again, and I remember, it's actually an iterable you have to feed it. So you feed it one argument, and that argument is an iterable. So what it is it's a list that contains the data frames that you want to join together. So this is proper. There we go. And now we can see our data frame contains both of those, where before we had df1 just has the hello, df2 just has the world. When we concat them together, now we get the combined data frame. But the problem with that is, if let's say df3 equals, we're going to define it as a dictionary, and it's going to be 0, like that, world. So this is basically what df2 looks like, but it's just got that extra column. So like this is similar to what it looks like. We have to close the quotes. So now df3 looks a bit like df2, but it's if we look at the type of df3, it's a dictionary. We look at the type of df2, it's a pandas data frame. So what happens when we concat a data frame with a dictionary? So we know that df2 is a data frame. We know that df3 is a dictionary. We cannot concatenate object of type dict. Only series and data frame objects are valid. So we have to convert the dictionary to a data frame. So that is done. I forget how it's done. There should be a method here to create it. So I don't think this works. No. Okay, yeah, so I don't remember how to do this. You can also do a dir to see all the things you can do, all the methods you can do. So maybe there's a to data frame, something like that. All right, I don't see anything like that. Okay, so we can convert a data frame to a dictionary, but I don't see how to convert a dictionary to a data frame. So I remember doing this before, I just forget how. This is basically what ChatGPT does best. So in pandas, how do I convert a dictionary to a data frame?
To convert a dictionary to a data frame in pandas, you can use the PD data frame converter.
Oh, I guess I did it right. It's just the structure of my dictionary wasn't right. So let's go back to that command that I did before. Let's see how that works. So this is how you do it, but the problem is my dictionary is not valid. It has to be so we have to have a row, and then we have to have a column. So let's do that. So let's redefine that dictionary. So this would be a row, and now we need to give it a column as well. All right, and now this should look about the same as df2. Yeah, so it should look about the same. So now we should be able to convert that. Oops. Must pass an index. All right, well, let's pass index 0. Oh, so obviously it's not that simple. I spent about 2.5 hours on it in the last video, and I threw all my work away. So we're not going to go with that. Hopefully we don't need to. And yep, we don't need to. So the code ran successfully. There were those warnings, but it did not prevent a data frame being generated. And now we can see the what? Well, that's okay. I wasn't expecting that. So I was expecting there to be a new file there. So let's try to get okay, so this is use case 1. Oh, this is still working. Okay. Interesting. All right, I'm not sure when that's going to finish, so let's move on with the reading. Problem resolution. To solve this problem, based on the approach described earlier, we need to end up computing the Pearson correlation index between all combinations of ports. It is certainly processing intensive, but brute force is your friend. So let's apply some force here. The good part is that collecting interference data is really easy. Now, one challenge is that there could be interfaces that have no traffic, and if that is the case, there is no way to differentiate because those will only show a correlation index of 1. So one caveat of this method is that we can only discover the topology for the interfaces that have traffic. Because of this, we will filter first those interfaces that have had no traffic during the period of data collection with the following routine. There we go. Looks good. It looks good. The output of the above is a list of the target interfaces, those that we will consider for our analysis. In our case, that list is 800 units long. The next step we have to do is to align the samples. The data collection process does not guarantee that in reality that the sample for two interfaces will have exactly the same number of observations. That is expected, but we need to have vectors of the same length to compute the correlation. So the first thing we have to do is to align the vectors. The more aligned they are in time, the more likely the correlation will be successful. You could also face the scenario that for a certain device you are collecting data every 5 minutes, and for other devices you are collecting data every 1 minute, so you have 5 times more observations from one. Ultimately, we need to align them to a common number of observations. We will apply sampling and interpolation to generate a new vector that is as close as possible to what the original vector would be, but with the target vector length. This process is an approximation, but is good enough to get us where we want. The following function will do that vector alignment process, in our case, to 200 observations per vector. If we observe the Rx vector in the next figure, we have columns that represent each of the interfaces for which we have received traffic data, 800 interfaces, and we have as many rows as observations we have created for the aligned vector, in our case 200. At this point, we have dropped the timestamp. The assumption here is that each observation will be reasonably aligned in terms of timestamp with the corresponding in other interfaces. There is no way to guarantee 100% precision, but it is also not necessary. We are doing a statistical analysis, and unless the deviations are very significant, the results will be acceptable. Now it is time to start preparing the calculation of the correlation. Let's recap. What we aim to obtain is the correlation of egress traffic from all ports with the ingress traffic towards all ports. So effectively, we need a matrix with 800 columns and 800 rows. This is what we will prepare for now. Alright, looks good to me. At this point, all correlations are still empty. Let's now compute the correlations. There are multiple functions in different Python libraries to compute Pearson correlation. Our challenge here is that we usually have large matrices, and some of those pre-existing functions tend to work well with 2 input vectors. In our case, we have many vectors. So we are going to use a custom implementation that has been optimized to work directly with matrices, which accelerates the calculation by orders of magnitude. We now have a 800 by 800 matrix that looks like above, with numbers between -1 and 1 that represent the correlation index between traffic out and traffic in for each of the interface combinations. Let's look at one example of how traffic looks like between 2 interfaces for which the correlation was computed to be 1. In this case, row 1, interface ET-1-1-1 in PE-1, and column 0, interface ET1-1-1 in C-1, using the following routine. All right. As you can see, both graphs look identical, and they are indeed because SANS is generating data in a way that it ensures that, based on the topology, egress traffic data for one interface will be the same as ingress traffic data in the connected interface. In your networks, the graphs will not be identical, but will be extremely similar in any case. If we visualize a histogram of the different correlation indexes, we can see that there is a large concentration between 0.9 and 1 with some much lower similarity. Alright, so let's try to get to that histogram before continuing. So this is still going. Now it's said that it will just keep going for a long time. I do notice there's a parameter here set to 10 and 4 hours. So I don't know if that means it's going to run for 10 hours. I hope that's not the case. We do always have the opportunity to delete these 2 cells here, and then call in the data frame that exists. We just have to change this and then delete these 2 cells, and we could do that. So I hope it doesn't take 10 hours to run. I don't have 10 hours, but we could keep reading and then check in back later. And if it's still working, there might be a point where I just want to go with the saved file. All right, but in the meantime, I need a quick break. Alright, I'm back. 43 minutes is a good length for a video, so I'm going to check this in one more time. Looks good, and let's try to get through some reading, and if I get through a fair bit of reading and then it's still dead, I might just end the video, and then when we come back, we'll load in the saved data. Now it is the time where we need to start making decisions. If all was perfect, the correlation between egress traffic and ingress traffic would be 1. But in reality, we cannot guarantee that. So what we likely have to do is to select a short list of candidate interfaces for each interface which have the highest correlation. Likewise, we can set a minimum correlation to ensure that we only select in the list interfaces whose correlation is high enough. In our example, we will pick 3 as the shortlist length and 0.9 as the correlation threshold. In your network scenario, this may need to be fine-tuned. We can also take advantage of the fact that if 2 interfaces are connected, you would expect that the correlation for traffic in both directions would be, in both cases, very high. So if we have selected a short list of candidates for each interface, we can check for each pair of interfaces if they are on their respective shorts lists and conclude that this is the most likely candidate to be the real neighbor. Alright, and I'll check back in. This is kind of a good stopping point because there's a full page of things to read, and then when we come back, there's a clear data object to get to. So I think I'm gonna end it here. Let's take a look at how this is going. Yeah, it's still going. So I think it's best to just stop this. We're gonna restart and clear all output, and then we're gonna delete these cells. All right, and then just load in the existing data. There's kind of no other way. It's just taking too long. We could clean up that append statement with a concat statement instead, and it would probably run a lot faster. And then we could just leave it as append for the one where there was difficulties. But this is ready to go. We can see we've got the interface. We've got that data object, and then the next one we need to get to is candidate underscore correlation. So we should be able to get all the way there pretty easily now that we're just using the loaded in data. Okay, so now we're doing a for loop that's taking a while. Okay, we've got a progress bar going. And this is out correlations. Is that what we're looking for? No, we're looking for candidate correlations. Okay, progress bar is at 100%. There we go. Oh, so we've got a okay. It's just an error. That's fine. All right, so we got everything to run up until there. So that's going to be it for this video. Stay tuned for the next one.